Hi, everyone. Let's get started. So if you don't know where you are, you found your way into the Next Generation SDN track. There's a few different themes for this track. One of the themes is going to be sort of what we're calling the Next Generation data plane. Stratum is one of the tools that we're using as part of the Next Generation data plane. There's also going to be some talks on how we can define data planes using languages like P4. There's also some work on the control plane side. How do we create SDN 2.0, 3.0, 4.0 architectures? How do we go beyond the work that's been done thus far? So the first talk in the session I'm going to be giving, it's going to be an overview to Stratum. For those of you that have been around the community for a while, hopefully there's not too much repetition, but this talk is really geared towards level setting this community, giving you a little bit of background, motivation for the project, high-level use cases, helping you to set the project in sort of the context of the broader ecosystem. And there's going to be some other talks about Stratum later today and tomorrow that also hopefully will be set up better by understanding where we're coming from. So let's get started. So the first thing to understand about Stratum is to understand the ONF. My name's Brian O'Connor. I'm an engineer at the Open Networking Foundation and have been there since somewhere between OpenFlow and ONOS on this chart. Worked with a lot of different operators and network vendors over the years. And at the ONF, we started with actually an interface that is going to disaggregate the data plane and the control plane. That was OpenFlow. Many of you probably read the spec, implemented the spec, seen boxes that did this. And we sort of thought, mission accomplished. We're done, right? We have a nice separation, a nice clean remote interface, and we're good to go. On top of that, we built a control plane, a distributed control plane called ONOS that gave us the performance that we needed to deploy SDN. We built an NFV and services solution on top of that called Cord. On top of that, we have an SDN fabric that's used in Cord and also leverages ONOS to deliver that. There's a few other projects like SIBA and others that you've seen and heard talked about already. So how do we get to Stratum? Well, Stratum's kind of coming back around the circle. Through this talk, I hope to motivate some of the reasons why OpenFlow isn't good enough for an evolving network environment, and also take a look at how the interfaces that we need to define between a data plane and control plane can start to be leveraged going forward. The other player that it's important to look at or understand for Stratum's genesis is Google. So as Amin mentioned, Google's run SDN at scale. They're probably one of the biggest deployers of SDN in production today. They've talked about a lot of different initiatives. They've talked about B4, an SDN-controlled WAN that manages primarily inner data center traffic, which Amin mentioned is growing faster than the internet. They've built data center fabrics in the petabits per second range that manage sites with hundreds of thousands of servers. And they've got a play using SDN in the peering metro. So I think that number is probably old. I think Amin said that number is more. But anyway, the point is that there's a lot of traffic going through networks, and that between the open source proof points that we've looked at, and between some of the proprietary solutions that we've started to see, it's no surprise that SDN is beneficial in many ways. Oops, wrong way. So, what are these benefits? Depending upon who you talk to, you get a different answer, but here are a few. First is SDN provides fine-grained programmatic control across all elements of your network. It gives you support for more complicated QoS or load balancing policies than you can achieve using traditional loosely coupled distributed systems. SDN enables optimizations in general across your network, that if you have to wait for convergence times and you have to wait for greedy algorithms to reach consensus, are not necessarily achievable. SDN also gives the opportunity to provide enhanced visibility up to a control plane and management plane for troubleshooting, monitoring, and system auditing. The other thing, and this is sort of a means big takeaway from this morning, is that SDN enables features to be deployed by the operator of the network at software timescales. So you can balance this velocity, being able to add new things in software, with the availability requirements that your network needs. So I won't spend too much more time on this, but hopefully this point is clear and motivated. So what's the catch? Why don't we see SDN across every network today? We published OpenFlow about 10 years ago. We have some control plane pieces. What are some of the challenges that have caused kind of hiccups in adoption? And I've broken these up into a couple different categories, but one of them has to do with programming interfaces. So we mentioned we had OpenFlow, but OpenFlow didn't come with a data plane pipeline specification. Every vendor out there who had an ASIC built a different pipeline, and that pipeline needed to be adapted to by the control plane. There were some efforts to try to solve this, and some precursors to the P4 work, like TTPs, or table type patterns. But we really never got to a point where control planes could assume homogeneous forwarding behavior. The second challenge in this area is that every vendor pretty much provided proprietary models for configuration and management. It started with SMP MIBs, then we moved to Yang models, but you still got to this problem where you were building your control plane towards specific network elements, not towards a generic network element. And finally, we noticed that the OpenFlow spec we thought was long enough and detailed enough, but people still find ways to interpret English differently. English is not a good programming language. And so without an open source reference implementation of OpenFlow, there was some disagreement about the way in which things could be implemented. What this leads to is control planes that are written and tested against specific hardware. It leads to effectively either vendor lock-in, which is the second point. So you test and build your components against a specific set of ASICs and platforms, or you get to what we have, which is a least common denominator approach, which is either something like Psi. We're going to take the subset of functionality we need for the Microsoft data center, maybe a few other people's data center, and we're gonna use that as our abstraction. Or we do something like we did in OpenFlow, where we leave the control plane interfaces somewhat underspecified. Something like flow objectives enables you a great deal of flexibility in the pipeline, but at runtime it's possible that what you've done is not realizable. So OpenFlow didn't really solve, and NetConf really didn't solve the disaggregation problem. It was an important first step, and through learning, through building control planes and building orchestration solutions, we're ready to come around again and take a look at the interfaces. Just a quick aside on OpenFlow, before you allow too many of these challenges to be taken away as SDN doesn't work, and I'm afraid some of these slides are going to appear as ONF says SDN doesn't work. No, OpenFlow is not going away just yet. There are a lot of vendors that are deploying OpenFlow-based solutions in production. Our plan is to continue to support OpenFlow and ONOS in our control plane solutions, and if you look at all the demos that we have, we're using OpenFlow today. It's going to take some time for these interfaces to mature. This is called the for a reason. Hopefully for hardware and software support in Stratum, we're looking 2019, and we already have some demos of this working. Google's also shown demos earlier in the year. And this work is largely improving upon what we've done before. There's nothing revolutionary here that's happening. We're just taking the same ideas that we've pushed forward in the past and making some improvements that improve their productization and generalizability. The next thing, back to the challenges, that we didn't account for when OpenFlow was first created. And that's the advent of programmable switching hardware. This is programmable ASICs, FPGAs, GPUs, NPUs, and networking optimized CPUs. And so one of the challenges is that OpenFlow is designed around traditional networking data plane protocols. So for example, Ethernet, IP, TCP, UDP, VLAN, MPLS, etc. And it means that if you want to add new protocols to your pipeline, you have to define those protocols in OpenFlow. That involves a change to the spec or a vendor-specific extension to the spec, which is not something that's conducive to more rapid evolution. Even if you say, this programmable chip stuff is not for me, the truth is a lot of the fixed function ASICs that you find today have some degree of user programmability, usually in the ACL table space. And it's important that control plane writers can tap that themselves. And it's not up to just the vendors to provide new capabilities for their boxes, new data plane protocols for their boxes. So what we need here is we need a contract between the control plane and the data plane that is mutable. Something that can be customized by the operator, not by the vendor. And it's important to have something that we can start with and agree upon it and build against. So have a pipeline. Psi is a good starting point. But define it using a language that is more precise than English or any other spoken language. And then move forward and enable vendors to customize, tweak it to either expose specialized features in your hardware or enable specialized services that they want to run. Ultimately, operators, if they can dynamically define their pipeline and data plane features, are going to be able to build out new use cases and extract new device behaviors. And the last thing I'll mention about some of the challenges with our existing interfaces before getting into what is Stratum and how we solve these problems is bringing SDN to production at scale. And we've seen that many operators have hit some scaling limitations when they bring OpenFlow-based solutions or NetConf-based solutions to their networks. And so a lot of the work that we've done in the OpenConfig working group on GNMI and in P4 Runtime working group have been on addressing some of these scaling needs. The other thing to mention, which is something that Amin mentioned as well, is SDN at scale means new requirements happen frequently, and we need to have solutions to those requirements quickly, which means a frequent update to all layers of the stack, including the switch OS. In order to do this, we need to have high degrees of monitoring and visibility from the boxes to understand what's actually happening in the network, whether this update is breaking things, and having interfaces that are well-defined, having interfaces that provide streaming telemetry, having interfaces that enable us to have forwards and backwards compatibility without changing major versions, are all things that we're trying to address in this next iteration of SDN. So the goal is to kind of tackle these things. The last thing I'll mention, which wasn't really considered or talked about when SDN was just starting, is this notion of migration. So we said, we have a new architecture with new interfaces, and people can just deploy them in greenfield. And if you go to the business guys, or if any of us had gone to the business guys at the start, they would have said that it's not really feasible to forklift your entire network. It's not going to happen. You have to figure out how you can upgrade one box at a time, provide incremental value, how we can upgrade one pod or one data center at a time, provide incremental value. And then, when this stuff works, when we gain operational experience, when we see some ROI, then we're going to move forward. And so the types of migration that we want to try to think about, if not address directly, are how do we go from fixed function to programmable chips? And by programmable chips, I mean in addition to new programmable ASICs like FPGAs, GPUs, TPUs, et cetera. How do we go from traditional networking to SDN? Traditional networking has a different model of working where we have control planes on the box. We don't have a centralized control plane. How do we go from my favorite networking vendor that I've been working with forever to someone else's boxes? Integrating that and making sure that you have the management, configuration, visibility working on the new boxes is an important step. So what it comes down to, at least from Stratum's perspective, is we need interfaces, models, and operations to be our consistent plane. And ultimately, if we can be consistent at one layer, we can start to roll in new programmable hardware. We can start to roll in new SDN-style concepts, and we can start to roll in new multi-vendor boxes and environments without having to forklift upgrade our networks. So what we want, what's the requirements that we can derive from some of these challenges? What we want is we want a control plane interface with abstractions for different types of chips, not just the fixed function chips, not just Ethernet, not just L2 and L3. We want well-defined interfaces and behavior, ideally with some reference code or reference semantics associated with those interfaces. And we want extensibility. We don't want a vendor to have to go and modify the protocol that we use in order to add new data plane capabilities. We want to have extensibility baked in from the start so people can prototype easily. We want common models for configuration and monitoring. This helps with the multi-vendor problem. And then we want common interfaces for operations. So the ability to do testing, debugging, certificate management, software upgrade in a multi-vendor common way is important. Where possible, having common platform abstractions helps reduce the amount of code that needs to be written. It also enables improvements by one vendor to benefit others. And then lastly, we want this to be open source. And the reason we want this to be open source is because it goes back to how do we get this into production and how do we get this updated every week. If you have to wait for somebody else to be rolling updates, it's going to be ultimately challenging for you to gain confidence and solve problems and have the velocity that you need in the ever-changing network that we're working on. So what are the requirements from SDN that we've gained? And this may be obvious. We're looking for high degrees of scalability. Networks ultimately are tens of thousands of devices at the largest scale. At that scale, you need everything to be automated. We can't have people logging into boxes and typing in credentials or SSHing into boxes and reading port stats. Ultimately, these things need to be collected proactively, and we need to be feeding them to systems that are monitoring the health of our network. These interfaces need to have high performance. We need to be using protocols that are optimized for the amount of data that we're actually transferring. Human-readable, text-based protocols generally aren't going to cut it at some of the scales we're talking about. And then, we need to have SDN decoupled in such a way that it can really be driven from a design perspective by the network operator. So the first interface that we're looking at solving some of these problems is called P4 runtime. P4 runtime oftentimes gets coupled with P4, which is why they're pictured here together on the slide. Although P4 is not the only language that you can use to model something that's controllable via P4 runtime. So in P4, typically we have a program that defines our pipeline. Typically that program will cover things like the parser, what data plane protocols or packets are covered. We typically have an ingress pipeline. So once packets are coming into the switch, what are the tables? What are the match action fields? How do we move things forward? Then typically they go into some kind of packet replication or buffering, and then we have the same thing on the egress side. This is a PSA architecture from the P4 runtime group, and I've only put it here as illustrative purposes. Ultimately, on top of this, we have something called P4 runtime, which is going to talk to primarily the ingress and egress tables, do things like write table entries for the pipeline stages. It'll do things as well like action profiles if you have certain failover behavior, ECMP or WCMP behavior. There are meters and counters that are part of the switching ASIC that can be exposed. And in some sense, there's some stateful elements as well. Some externs, some registers. We can control some degree of packet replication and queuing through this setup as well. You could take PSA and replace it with a different architecture. You could take P4 and you could replace it with a different pipeline definition language. P4 runtime is agnostic to the actual language semantics, and it merely provides a common programmatic interface to update tables and the standard types of things that we do in networking gear. The other thing I want to highlight here is that P4 is not just for programmable switches. There's a lot of associations with P4 and FPGAs or P4 and programmable ASICs. And yeah, in those cases, it works pretty well as a mechanism for defining your pipeline. But P4 is also useful in the context of defining a logical table structure that works across multiple physical ASICs. For example, if your logical table structure is import filtering followed by L2, followed by L3, that's probably a pipeline that you can match or handle in pretty much any silicon you can buy off the shelf today. Now, the actual location of those tables, the capability of those tables, the order of those tables may be different. But if your control plane application suite that is targeted at routing has a pipeline definition that is common, now you can start to take control plane code and reuse it across multiple ASIC types. And maybe the other things, maybe some of these boxes that aren't covered as logical tables are exposed as other logical tables, and you have other apps that can be turned on depending upon the capabilities of your ASIC. So the key thing here is that in addition to programming tables, and in many cases, P4 is used to map logical table to hardware resources in the FPGA or programmable ASIC case, P4 can also be used to map logical tables to physical tables in more traditional fixed function ASICs. And the big benefit takeaway here is we still have an advantage in that we can write control planes against a single pipeline and then rely on a compiler and a runtime like Stratum to do the mapping from logical to physical table. So P4 and P4 runtime are great. Maybe you've seen this punchline before, but they certainly don't do everything. There's a lot in configuration, monitoring, and operations that aren't covered, and intentionally not covered, because it's not P4 runtime is not meant to be a catch-all. So what are the types of things that also need to be considered? Well, QoS queue setup and scheduling configuration, CERDES configuration on various ports, the channelization of things like QSFPs, setting fan speeds, managing thermal profiles. It's worth noting that many individual boxes have thermal profiles that only consider the box. Oftentimes in data centers, you want to also consider the thermal profile of the rack or the row or the whole data center, which is difficult to do if you're optimizing for on-the-box temperatures. Power supplies, monitoring what the power loads are as well as failures. Port state mapping, so mapping from your front panel port to your ASIC port, having some knowledge of that, as well as doing LED control. And if you think about LEDs in the context of what can you do centralized, yeah, you can do traditional blink if there's data flowing, but you can also think about how can I use LEDs to help a technician wire ports together? How can I use a technician, LEDs to, once I've verified a topology, show you red means that this port is actually wired wrong or not connected. So there's new things that you can do if you expose that capability. Monitoring sensors like temperature are important for things like more globalized thermal profiles. Managing the management network, doing software upgrade and deployment in automated ways, and the list goes on. So there's a bunch of other stuff that is on the box that is important to control in some way, whether you're doing on-the-box control or off-the-box control. And this is where OpenConfig, GNMI, and GNOI are here to help. So just a quick overview of these. So GNMI, you can think of it as an advanced or enhanced configuration protocol. It covers configuration and management of the devices. We use a declarative configuration language, specifically Yang, to define the capabilities of the boxes. And then what happens is the Yang gets converted to protobuf, and then the protobuf is used over a gRPC connection. We use gRPC instead of things like HTTP or SSH because the binary encoding helps with transmission, as well as gRPC enables streaming capabilities. I know there are extensions to both RESTconf and NetConf to support streaming, but out of the box with gRPC, we get streaming telemetry for things like port events, power supply or fan failures, temperature events, et cetera. So you can think of GNMI as an extension to largely netconf with gRPC backend and streaming capability support, subscription support. GNOI covers the network operations, things like certificate rotation, things like access policy control, bit error rate testing, and other operational reboot software upgrade, stuff like that. In general, Stratum also is pushing forward a set of vendor-neutral data models, which is a subset of OpenConfig, along with a few augmentations. But these can also be augmented by vendors to expose capabilities of their boxes. And those capabilities can then be interpreted by a management or control plane. So putting it all together, we have a pipeline defined in P4. We have a pipeline that's controlled using P4 runtime. We have configuration and telemetry using a subset of the OpenConfig models and GNMI, and then we have a set of operational interfaces under the GNOI umbrella. And so that's how we define this set of interfaces going forward. And then the Stratum project is a lightweight and production targeted implementation of these interfaces. So it's worth noting that in all three of these cases, P4 runtime, OpenConfig, or GNMI and GNOI, we use gRPC as the backend transport. And that means that from a control plane or management plane perspective, you have the capability or flexibility to use any programming language of your choice for the most part. And you're not tied to specific libraries that have been built against these various protocols. So let's move on to Stratum. And in Stratum, what's the vision? So we have interfaces. We want to implement those interfaces. But we also want an open source reference implementation of those interfaces. And so the vision here is Stratum works on multiple silicon products. So we don't want to be tied to a single ASIC or a single ASIC family. We want this to work across multiple platforms. We want different OEMs and ODMs to be able to take this code and reuse it. We want to see this widely deployed in production. This isn't just a reference implementation that people can use in their labs, but something they can take and actually use in deployments. Ultimately, we think that doing this will help enable the adoption of these APIs. Oftentimes, like creating the libraries and creating the mappers that adhere to these APIs is one of the hardest parts. So having reference implementations that work, that people can take, can help create a nice feedback or synergy between the standardization effort and protocols. In general, if people want to take these interfaces or Stratum and put them into black box products, that's okay. White box is also great. And ultimately, the goal here is share the interfaces, share the technology, get us established on a common baseline where these boxes and these interfaces are effectively table stakes, and we can focus our efforts on some of the cool stuff on the hardware side and some of the cool stuff on the control plane side. So pictorially, what this looks like is we have some switching hardware, some kind of switching chip like an ASIC. We have a few interfaces, the OpenConfig suite and P4 runtime, and ultimately this plugs into your control config management and monitoring plane, just like a Lego brick does. So instead of having to create a proliferation of drivers at your control config management layer, or just have one driver and be locked into a single vendor solution, ultimately if we can plug Stratum and P4 runtime and OpenConfig boxes into these things without too much effort, we're in a really good place to reestablish kind of a pathway towards innovation. From a management side, this talk isn't really focused on them, but ONF's Trellis fabric already has support for P4 runtime and GNMI, and then Google's production Jupyter fabrics also are starting to leverage these interfaces. So, from a box side, okay, now you've got the same interfaces that can plug into two different fabrics. There's a few other fabrics and solutions that I'll talk about later as well. And then from a control plane side, now it becomes easier, and the barrier to entry is lower. So the next part is, how do we support traditional switch OSs? Because maybe the SDN part was clear, but another thing that we mentioned before is migration is a critical piece to consider in this. And so Stratum can help initially in the context of traditional switch OSs by providing a clear pipeline definition. That's one probably often overlooked area. When you have someone who's writing a switch OS today, they go to like a fat stack of papers written by ASIC engineers to discover the pipeline, and then ultimately they try to figure out the SDK, and you have someone that spends a year or more optimizing their particular solution for a given ASIC or platform. So one clear benefit is if you defined your pipeline more clearly in a language that is consumable programmatically, it becomes a lot easier for a network engineer or control plane engineer to reason about a pipeline and program against it. The second initial benefit is a lot of the network OSs that we're looking at today don't have support for programmable chips. Or if they support programmable chips, they don't expose chip programmability to the control plane. For example, they might expose a fixed pipeline, and then that's it. That's what you get, because that's the API that's expected by the network OS. So in this case, what we're seeing is that if you layer Stratum in as a data plane agent beneath the traditional network OS, you can have support for programmable chips, and you can have support for a pipeline definition. And we're actually talking with some projects like Sonic about how we can make this happen underneath Sonic's control plane layer. The next thing that you can do is you can start to experiment with SDN-style techniques. If you want to do centralized traffic engineering, if you want to do monitoring, if you want to do diagnostics or troubleshooting, you now have the same interfaces that are exposed to your network OS that can also be exposed to a switch OS. If you're worried about the SDN OS or troubleshooting tools kind of messing with things, you can enable read-only access, or you can firewall these protocols using authorization policies. But ultimately, you can start to gain some benefits by collecting telemetry and stats, and ultimately, influence the policies that are on your box without having to running in kind of a hybrid mode. This also enables a more easy facilitation of existing services. Obviously, if you're going to write your DHCP and BGP client against something that's specific to your network OS, you're not going to have an ability to move it as easily. But if you start to write new apps against the lower level next-gen SDN APIs, what you can start to do is think about, well, do I need to be running this service on the box? Could I run it somewhere else? And what this can allow is maybe decommissioning a service from the box, putting it somewhere else. Maybe there's a service that you're running in your, or prototype at your SDN network OS layer that you realize, like, this could actually be done locally. Maybe we don't need to be handling LACP messages for lag support on the SDN controller. And those apps could be pushed down. So they could be prototyped centrally, pushed distributed. They could be traditionally run distributed and moved centrally. But ultimately, the goal here of having interfaces that are clear, hardware agnostic, and remote or local agnostic is the ability to move things to where it makes sense. So what this results in is kind of a next-gen SDN picture. Stratum fits into a picture where you've got leaves and spines. Note that we can use different profiles depending upon a role of a switch within the box. We're not confined to one pipeline for a whole network. We have a clear set of interfaces that provides a logical separation between our network devices and our control and management plane. And ultimately, how we deploy these control and management planes is a separate story. We can deploy some of these services on the boxes. We can deploy some of them in traditional commodity compute infrastructure. Ultimately, the control and management plane needs to plug into inventory, global orchestrator, OSS, BSS, et cetera. And that's where kind of the rest of the next-gen SDN picture goes. And there'll be a talk, I think, on Thursday about how ONOS is looking to evolve towards filling some of this gap. But ultimately, with Stratum, the thing to take away is different profiles for different devices, multi-vendor, multi-chip hardware, and a common set of interfaces that enable control management operations to occur. So a few integrations that we've done so far, and a few that we could do. The one that we've gotten sort of farthest along with on the open source side is an integration with ONOS. And there's a demo that you can see down the hall, and you may have seen it in Europe or in China. But what we've done here is we've added support for the protocol layer, P4 runtime, GNMI, and GNOI at the southbound of ONOS. This just allows us to talk to Stratum-based devices, but doesn't necessarily do anything with them yet. We've also plumbed P4 runtime into our flow rule and flow objective subsystems. So flow rules and flow objectives are ways to either target individual tables or target that underspecified pipeline I alluded to as part of the earlier challenge. Then we can translate from ONOS's core abstraction, which is those two, flow rules or flow objectives, down to the P4 runtime program. Ultimately, these translation services need to be built against a specific pipeline, and the pipelines in our case are called pipe comps. It's basically a P4 program plus some code that understands how that P4 program adapts to the ONOS core abstractions. At the ONOS northbound perspective, then you have a choice. If you want to be pipeline agnostic, if you don't care about the switching pipeline, you can use flow objectives. If you know exactly what pipeline stage you want to use and what rules you want to craft, you can write an app that is aware of the P4 program. These devices also plumb into ONOS's topology service as well. For GNMI, again, that's a protocol implementation. That plumbs in to ONOS through behaviors currently. So we have capabilities to get port statistics, port state, et cetera, through GNMI and the open config models. We're looking at ways to see if this can also be plumbed into dynamic config. But as for today, the behaviors mechanism is working just fine. And then GNOI actually is still a bit of a work in progress, to be honest. But ultimately, that's going to talk to some of the administrative services to do software upgrades and certificate management. So what about other control planes? What about things like FRR? FRR is a good example because it uses the Linux kernel stack or rather, Linux IP tables for managing networking state. So in general, for tools like FRR that use IP tables, what you can do is you can run your control plane on top of the Linux stack. So for example, BGP, RIP, OSPF, whatever you want if you're FRR, using Zebra to manage your FIB, and then push that to kernel routing tables. Once they're in the kernel routing tables, your pipeline is somewhat constrained, but we can use netlink to extract information from the kernel routing table. And one of the things that is currently being worked on by one of our community members is this layer. So basically understanding the kernel routing table pipeline, having a target P4 pipeline that matches the capabilities, and then using a combination of P4 runtime and GNMI to provision the forwarding entries down to ultimately Stratum and the chip. So in general, yeah, this pattern can be adapted in cases where you're using the kernel table. What about Sonic? So as many of you may be aware, Sonic is a project that's centered around the switch state service, Redis database. They expose an AppDB to the northbound. This gives you an ability to program some various applications as well as configure the box. And then there's a synchronization database that ultimately maps the forwarding entries down to an API called SI, Switch Abstraction Interface. How can we adapt to this? So one of the things we can do, and something people have already done, is model the SI pipeline or capabilities using P4. We can compile that P4 down to the given ASIC target that we're looking at. And then ultimately, this is the sort of to-be-built stage. But you can go from the SI headers, which are things like add this L2 rule, add this L3 rule, down to the P4 translations on top of the SI pipeline. There's also some models that SI has that may not be covered in OpenConfig. So I don't know exactly how we pull those together. But this is generally meant to illustrate that in cases where you have a specific ASIC SDK that you've built your control plane against, if you can model your ASIC vendor's pipeline in a common way, then the adaptation layer from ASIC SDK down to something like Stratum is pretty straightforward. Once you do that, you have flexibility to start changing the ASIC underneath. You have the ability to start exposing your ASIC interfaces up to other services that are not necessarily built on top of your SDK. And then ultimately, you're also free to mutate or evolve your pipeline over time. And what might that look like? So something that Mellanox and Microsoft have been working on within the OCP and Psi community is a pipeline they call FlexPsi, or PsiFlex. And what this does is it takes the traditional Psi pipeline, things like ingress port filtering, L2 bridging, routing, tunneling, et cetera, and it defines them as fixed function tables within an architecture, a P4 architecture. What you can then do is you can have some flexibility to inject custom logic between these various stages to add things like INT headers, in-band network telemetry headers, to add new types of encap or decap, or to add pre-filtering or post-filtering rules to your standard Psi pipeline. So if Psi covers most of your use cases and your control plane is written against Psi, your control plane can target these read-only tables, and then your new applications can start to target some of the green tables that you write. One area that we struggle a little bit with is the parser. So the parser has to be read-write in this case, although there's elements of the parser that if you change or remove, you can break things. And this is where I think we're working a lot with or we're starting to work with the P4 community on what does a modular and composable pipeline infrastructure really look like. But what this is meant to say is that you can imagine parts of your pipeline are going to be targeted by your existing control plane programs, and then you can enable some degree of accessibility or programmability to new applications through architectures like PsiFlex that enable injection. There's also architectures that Barefoot has proposed that are a little bit more, you could use something like switch.p4, which is a standard switch as your baseline pipeline, and then just take out the parts you don't care about, or ultimately your control plane is not going to use, and then focus on what is my actual contract between control plane and data plane. And this is definitely an area that we're exploring and hoping to put forward as part of the Stratum project. So hopefully you have a better sense now of some of the use cases or the spectrum of use cases that we're looking at. Obviously a lot in the SDN space. Stratum plugging into proprietary network OSs. Stratum plugging into ONOS, talking to Trellis, or ultimately maybe some of the cord cases like MCord, LTE, or 5G looking forward. So in these cases, a standardized pipeline and an ability to offload certain functionalities is critical. But we're also looking at the sort of thick switch or traditional router case where you have an embedded management and control plane, like your BGP or OSPF agents running on the box, using Stratum as a mediation layer for multi-platform, multi-ASIC environments. Ultimately, I think hybrids of these is where the most interesting use cases are, and also kind of the most kind of next generation architectures. Maybe they're things that people have been doing for years, and we just are now calling it something different. But thinking about ways in which we can mix and match these in various deployment scenarios is definitely one of the things we're starting to undertake as a broader community. So the next thing is just to focus on a few use cases. Some of them from some of the different community members, just to give you a flavor of some of the things we think Stratum will enable. So the first thing is looking at zero-touch provisioning. So this use case is one that comes from Google, and it looks at, do we have all the interfaces in place so that I can have a technician walk into a data center, plug in some SFP modules, plug in a power supply, and be off and running. Maybe scan the scan the SKU into a database. But ultimately, network design is going to happen offline. This is where we define our topology. This is where we define our pipeline or contract. And this is where we define sort of the various roles that each of the boxes within the network is going to play. Once that happens, we push that over. In some sense, there's also work out of scope from Stratum. Can this be done automated? We'll see. But ultimately, once you push those requirements down and we plug things in, we want this process of bootstrapping a device to be as seamless as possible. So this means using things like ONI to automatically load a switch image and install it, getting the latest version of the switch OS and the components that are supposed to be running, then configuring the box, channelizing the ports, setting the port speed, setting queues and QoS, pushing the pipeline down, and then starting the data plane. That's where we start to load fib entries and other rules for telemetry or multicasting, ECMP, fast failover, et cetera, to the box. Ultimately, the data plane is going to run, and then a week later, it's time to upgrade the software. So being able to either do that upgrade in a hitless way, and I think one of the later talks will address how Barefoot looks at this problem, or in cases where you can't do upgrades in a hitless way, maybe there's a problem with the pipeline. How do we drain traffic off devices, take them out of service, do a cold reboot, and then bring them back up? When you get that first service call, do you have enough information to pinpoint the problem, figure out where it is, and then take that box offline, upgrade the hardware, software, or whatever needs to happen. So ultimately, this is sort of the life cycle that we want alongside some monitoring and troubleshooting tools. Stratum's goal really is to enable these tools to be built. Another use case that we're looking at comes from NTT Labs. And what they want to do is, this is an SDN style use case. They're looking at how do we flexibly scale up or scale down our VNF deployments. And what they want to do, specifically with Stratum, is if you use in-band network telemetry to discover the latencies and also drop rates of certain VNF instances, then you can start to figure out experimentally where those VNF limits are, or when there's a VNF that's starting to have certain failures. And then if you can feed that information back to your orchestrator, you can spin up multiple instances of the VNF and start to shard traffic between those multiple instances. And we can do that for things like CPE or IPS, et cetera. This can also be used to set lower bound thresholds. So when certain VNFs are performing better than expected or better than needed, you can potentially scale down automatically those things as well. Oops, wrong way. The other one has to do with DDoS detection. So looking at flow stats from the device. This is a kind of standard SDN style use case that Stratum also enables, where you can look at certain traffic flows if you detect anomalies in certain patterns, forward that traffic to a mitigation function seamlessly, and then either allow it to continue to proceed, rate limit in some way, or black hole or reject it. Another use case is in the edge router. So currently, there's lots of functions that sit in these edge routers. Some operators are not ready to completely disaggregate these just yet. But there are advantages to be had by making these functions separated from the actual data plane interfaces and configuration interfaces that we have. So certain things like PPPoE termination, being able to do some of that in P4, authentication, AAA, et cetera, doing that in control plane, maybe on the box. Other things around traffic shaping. There's sort of a blend of being able to offload some of this to the box using a P4 program and doing some of it using control plane rules that sit on the box. The other use case I'll just mention comes from Tencent. And Tencent is looking at how do we sort of disaggregate our data center fabrics. And if you look at kind of your traditional switch OS that sits on a big router, that starts to look like your data center's SDN controller, your local controller. If you look at the fabric cards in a traditional router, those look a lot like your spine switches in a Clo fabric, a white box Clo fabric. And if you look at your line cards, that looks a lot like your leaf or top of racks. And so you can start to build fairly big data center fabrics that look like traditional routers that have been disaggregated across these name boundaries. And these can still use things like BGP, MPLS, ISS to communicate with other clusters. And then those control packets would go up to the control plane functions appropriately. So Tencent's view, again, I'm presenting a slide on their behalf, is centralized control doesn't mean the entire network has one controller. This is also what Amin said earlier. We can have a hierarchy of controllers that extends all the way down to the switches, and it's you as a network operator or designer have a choice of which functions should be placed where. One of the things that they're planning to do in this use case is to opt for a network of controllers, and some of those controllers look a lot like a cord pod. Ultimately, having freedom to use different protocols or RPCs is important to them. Another important aspect of the overall solution is an interoperability between various networks. So hopefully this gives you a little bit of a flavor of some of the things that community members are starting to do. Some of it looks like SDN in restricted contexts like this. Some of it looks like thick, regular switch OS traditional networking, like NTT's thick router. Some of it looks like pure play SDN in the case of Google's context. And ultimately, the UPAN reference design, which the ONF is published this week, is looking at best of breed hybrid style solutions that enable a disaggregated control plane and a disaggregated data plane. So getting to Stratum. So Stratum is it's billed as a lightweight, thin switch OS. But what does that actually mean? So it means we have a kernel running. This is a Linux kernel. A modern Linux kernel will do. We also are working on bundling this with Open Network Linux, but that's not a requirement. And in some cases, Stratum will be running other OSs. We have some switch chip drivers and platform drivers that'll be provided by the vendors, or we'll use the default ones in Linux. And ultimately, we're going to get some kind of SDK or platform API from our vendors. In the case of ONL, maybe that platform API is ONLP. Maybe it's the user/dev file system. Could be EEPROM, et cetera. On the switch side, what we do is, in the case of fixed function ASICs, we have a level of abstraction on top of the ASIC capabilities, like layer 2, layer 3, ACL, et cetera. And that ultimately, we leverage a component called a table manager to help do the translation between the L2 or L3 constructs in the SDK and the higher level P4 defined pipeline. So table manager is primarily what's helping us at runtime do that logical to physical translation. And then that all gets encapsulated in something called a node in Stratum. On the platform side, we're looking at leveraging the APIs that we have, like ONLP, to provide common access to things that are not switching chip related, things like fans, QSFP power supplies. And then a chassis manager is something that your ODM or OEM will provide that will ultimately tie things together. It'll tie the platform pieces and the ASIC pieces. It'll do ASIC initialization. It'll manage serialization, deserialization profiles, and it'll manage the front panel port to ASIC mapping. So this is code that is going to be specific to your vendor. One thing I'll note is that in the case of programmable ASICs, the logical to physical resource translation typically is going to be something that'll be the output of the compiler. And in those cases, things like L2, L3 don't make a lot of sense, but you'll have things like a table manager as well as packet IO in the programmable ASIC or FPGA case. On top of that, we have a common interface layer we call switch interface or switch broker interface, which enables us to have a common implementation of P4 runtime, GNMI, and GNOI. When I say switch broker interface, what I mean is not something like SCI. I don't mean that there's any semantics or abstractions that are built into this interface, but rather it's really like a broker between a common northbound implementation and southbound implementations. So things you could expect. Flow write to chip 1 would come into P4 runtime. P4 runtime would realize this is targeted at device 1 or chip 1. And then the switch broker interface would basically pass this message down to the node implementation for chip 1. If you had a new pipeline for chip 2, P4 runtime would receive the new pipeline, and then using the device ID in P4 runtime, we'd target it at the appropriate ASIC. If we want to set a new port speed on chip 1, GNMI would use the switch broker interface to route this to the appropriate place. And if we wanted to restart the chassis, that would be done accordingly. So really what the switch broker interface is it's a subset of our common interfaces that are specifically related to calls that need to hit hardware. So things like mastership arbitration gets handled in a common way. Authentication, authorization handled in a common way. Setting up streams and subscriptions happens in a common way. But things like writes and reads, gets and sets that need to be passed through look a lot like the P4 runtime or GNMI method calls. Just a quick overview on the implementation. So implements P4 runtime, GNMI, GNOI. Can either be local or remote, either using loopback interface or remote IP connectivity. Stratum's a C++ project that runs as a Linux process in user space. We can distribute it with ONL if you want, or you can bring your own OS. And we build it using a project called Bazel. Oops. So we basically started with Google, seed code, some production requirements, ONF with a community, and a sort of a desire to start to reinvent the data plane and control plane interface, and we got Stratum. But together, these organizations, they're not gonna move an industry. And what we've done is we've partnered with a broad range of providers. On the operator or service provider context, we have Google, Tencent, China Unicom, NTT, Turk Telecom. In the sort of network solutions provider, we have Big Switch, Ruji, VMware, BISDN, PL Vision, OSI. And the ASIC vendors, I'll let you read, Switchbox vendors or ODMs, and then other open source projects. The other thing that I'm pleased to announce is, as of this morning, we've added Juniper to the Stratum project, and there's a few other members that are also in the pipeline. One thing I wanted to just call out is, people ask, okay, you've got a nice big slide, but who's doing the work? How is that? How is this mapped to contributions thus far? And so one of the things I just want to spend a brief minute on is companies that have contributed thus far. If we look at Google, a lot of the seed code comes from them, and the use cases I described above. Tencent and NTT are both actively looking at using Stratum in near-term use cases. Big Switch is a big proponent that's been helping us with the platform abstractions. ONLP v2 they've been a big driver behind that with the community. VMware is looking at how GNMI can be used for on-the-box type applications and on-the-box control plane. BISDN has been looking at that mapping between Netlink and Stratum, as well as some of the common code. PL Vision, common code, OSI has been looking at documentation. Juniper just joined, but we expect them to be joining on the ASIC front. Barefoot, Broadcom, and Mellanox have been actively working on porting their ASICs to Stratum. Delta, EdgeCore, Inventec, and Noviflow have been looking at porting their boxes. Noviflow has also been helping in the common code areas. And then we're actively working with ONL, P4, ONOS Cord, and SDKLT. So it isn't everybody just yet. The project is still growing. But we went from a team of probably about 6 to 8 people when we started around May to a team, an active contributing team of around 40 at this point. So where are we going? Stratum is nearing the end of what we call a pioneering phase. So the pioneering phase is the initial reference implementation of some hardware and software platforms and some infrastructure. What we hope to do within the next month or so is move into what we call the member preview, where any employee of any member company can download the code, access it, and start to play with it. We expect to see expanded platform support through that point, as well as additional feature development, maybe host some hackathons. At some point in 2019, we're expecting some production and field trial deployments on some of the cloud and telco operators that have partnered with us thus far. And we're looking at an open source launch sometime around the middle of next year. At that point, this becomes a community project, and we hope that there's a sufficient foundation and usability that people will be able to take and ultimately use and deploy. So the current status, we're working towards the end of the member preview. We have reference platforms from 2 ASIC vendors and 3 platform vendors. Those are Barefoot and Broadcom, and then Delta, EdgeCore, and Ventec. We expect another 2 or so ASIC vendors and a few more platform vendors in 2019. And then this number should be 7. We've added 7 new member companies since our open source launch. And we've had 2 code releases to the pioneering members. The 3rd release will be the exit of the pioneering phase. I'll skip this slide in the interest of time, but it basically shows how over the 3 releases we've been evolving platform support. And then from a roadmap, we plan to open source Stratum in 2019. That's a high-level major objective. We also hope to get this into 1 or more production deployments. And then a 3rd objective is synergy with other switch OSs. This is traditional SDN-style OSs like ONOS, as well as having the community pick this up and use it in the context of more conventional switch OSs. There's a bunch more talks on Stratum throughout the day. So this is the track if you want to learn more about what's actually happening through the various vendors on the pipeline side and device side. And there's a demo in the exhibit hall if you want to take a look. I'll just leave this slide up here. The interfaces are already open. This is a link if you want to get information about joining the project. And there's a public mailing list for major updates.